Somewhere in the vaults of the world's museums sit 300,000 clay tablets, a library of the first human thoughts ever written down. And for over a century, only about 75 people on Earth could read them. Then, in a lab in Tel Aviv, someone asked a strange question. What if a machine could read what almost no human alive still can? To understand why that question matters, you have to go back further than almost anything we consider ancient history. Long before Egypt raised its pyramids, before the first stones of Stonehenge were set upright, a civilization was already writing things down in the marshy floodplains between the Tigris and Euphrates rivers, in a land the Sumerians called the cradle between two rivers. Around 4,500 years before our era, the Sumerians built what many historians consider the first true cities on Earth. And somewhere in that explosion of temples, canals, and trade, someone pressed a reed stylus into a slab of wet clay and left behind a mark. That mark was the beginning of writing itself. The system they invented is called cuneiform, from the Latin word for wedge-shaped, because every character was formed by pressing the tip of a cut reed into soft clay at an angle, leaving behind a cluster of wedge-shaped impressions. It looks, to modern eyes, like a field of tiny arrowheads pressed into stone. But within those wedges is an entire world. Tax records, love letters, court rulings, recipes for beer, contracts between farmers, prayers to gods whose names have not been spoken aloud in thousands of years. And, woven through all of it, some of the oldest stories human beings ever told, including fragments of the Epic of Gilgamesh, a poem about a king searching for the secret of eternal life, a poem so old it may be the very first great work of literature our species ever produced. Beyond writing, the Sumerians are credited with a staggering list of firsts that still shape daily life today, whether we realize it or not. They are believed to have developed one of the earliest systems of mathematics, including a base 60 counting system that survives, almost invisibly, every single time. We glance at a clock and see 60 minutes in an hour or 360 degrees in a circle. They organized early forms of law with codified rules governing property, marriage, and commerce that predate the more famous Babylonian law code of Hammurabi by centuries. They built irrigation canals that transformed a dry floodplain into farmland capable of supporting dense, permanent cities, something that had never really existed at that scale before. In other words, the tablets scholars and machines are now racing to translate are not simply curiosities from a distant, primitive past. They are administrative and literary records from a society that essentially invented the template for organized urban civilization as we still understand it, which is exactly why every additional tablet that gets translated has the potential to reshape our understanding of how complex human society first got off the ground. Cuneiform was not used by just one culture. Over roughly 3,000 years, it was borrowed and adapted by at least 15 different languages and peoples across ancient Mesopotamia, including the Sumerians, the Akkadians, the Babylonians, the Assyrians, the Elamites, and the Hittites. It is, in a very real sense, the ancestor script of the ancient Near East, the way Latin letters underpin dozens of modern languages today. And Sumerian itself holds an especially strange distinction. Linguists call it a language isolate, meaning that, unlike English, which is related to German and Dutch and dozens of other languages, Sumerian has no known relatives at all. It stands alone in the historical record, spoken by no one for thousands of years, understood today only through the patient reconstruction of scholars piecing together fragments of clay. For most of human history since Sumer collapsed, these tablets sat as silent, indecipherable objects. Museums accumulated them by the crate load throughout the 19th and 20th centuries, pulled from the sands of Iraq during colonial-era excavations. But having a tablet in a glass case and being able to read what it says are two very different things. The story of how humanity finally cracked this code is, on its own, one of the great intellectual adventures in history. It began in earnest with something called the Behistun Inscription, a massive monument carved into a cliff face in western Iran on the order of the Persian king Darius I, around 500 years before our era. What made the Behistun Inscription so valuable was that the same message had been carved 3 times in 3 different scripts: Old Persian, Elamite, and Akkadian cuneiform. Scholars in the 1800s realized that if they could crack the Old Persian version, they might use it as a key to unlock the other 2, in much the same way the Rosetta Stone had allowed Egyptian hieroglyphics to finally be read a generation earlier. It worked, eventually. Old Persian fell first. Then, slowly, painstakingly, over decades of comparison and educated guesswork, cuneiform itself began to yield its secrets. But here's the detail that tends to shock people when they hear it for the first time. The full decipherment of cuneiform was not a single triumphant breakthrough. It was a project that stretched across more than 2 centuries, beginning with the first attempts around 1802, and not considered essentially complete until as recently as 2022. 220 years. Generations of scholars, entire academic careers, spent chipping away at a puzzle assembled from broken clay fragments, missing pieces, damaged inscriptions, and a writing system that changed its shapes and conventions across 3,000 years of continuous use. And even with the code technically cracked, actually reading a tablet remains brutally difficult work. Cuneiform is not simply an alphabet you memorize and then apply. It combines 3 different systems at once: logographic signs that represent whole words or ideas, syllabic signs that represent sounds, and in some later versions, something closer to an alphabet. A single wedge-shaped symbol might mean 5 or 6 completely different things depending on context, on which language is being written, and on which century the tablet comes from. It is also, crucially, a handwritten script, carved by individual scribes with individual habits, meaning no 2 tablets look quite the same, the way no 2 people's cursive handwriting looks identical. Add in the fact that thousands of these tablets are cracked, chipped, worn smooth by 4,000 years underground, or shattered into fragments scattered across different museums on different continents, and you start to understand why, even in the 21st century, only a small circle of highly trained specialists in the world could reliably read this material. New Scientist once reported that figure at around 75 people capable of reading cuneiform fluently, 75 people standing between humanity and the deepest written record of its own past. This is the exact bottleneck that a small team of researchers at Tel Aviv University decided to attack, not with a chisel and a magnifying glass, but with a neural network. The project began almost humbly as a master's thesis. A researcher named Guthers, working alongside colleagues in computer science and archaeology, set out to build something that had never quite existed before: an automated translation engine that could take Akkadian cuneiform, one of the 2 major languages preserved on these tablets, and translate it directly into English. Not transliterate it, not offer a rough guess. Actually translate it the way a tool like a modern language translator converts French into English, except aimed at a language nobody living has spoken as their native tongue in roughly 2,000 years. To understand why that is such a difficult technical problem, it helps to know a little about how these systems actually work under the hood. A neural machine translation model does not memorize a dictionary of fixed word for word, matches the way an old-fashioned phrasebook might. Instead, it is shown enormous quantities of paired examples, a fragment of source text on one side, and its correct, expert-verified translation on the other. And over the course of training, it gradually builds up an internal statistical sense of which patterns of words in one language tend to correspond to which patterns of meaning in another. The challenge with ancient Akkadian is that the training data available is minuscule compared to what a system translating French or Spanish would have access to. There's no equivalent of the internet's worth of Akkadian text sitting around. Every single example the model can learn from had to be painstakingly produced by a human expert first, which means the entire project rests on the shoulders of roughly 2 centuries of prior scholarship, digitized and fed back into the machine as its only teacher. That is part of why this achievement is so significant. The researchers managed to build a genuinely useful translation tool for one of the rarest, lowest resource languages that has ever been fed into a modern machine learning system. The team trained their system on the small but growing body of cuneiform text that had already been transliterated and translated by human scholars over the preceding 2 centuries, essentially teaching the machine by feeding it every example of correct, expert-level translation available. Once trained, the model was able to take previously unseen fragments of Akkadian text and generate an English translation, sometimes in a matter of seconds, work that would traditionally require a trained Assyriologist hours, days, or in the case of thornier fragments, months. The results of this research were formally published in the peer-reviewed journal PNAS Nexus, produced by Oxford University Press, which matters more than it might sound. It means this was not a flashy tech demo or a viral social media claim. It went through the same rigorous scientific review process as any other serious academic finding, checked and challenged by other experts in the field before being accepted as legitimate research. The scale of what this technology could eventually unlock is difficult to overstate. Of the roughly 300,000 cuneiform tablets that have been recovered and cataloged to date, only around 10% have ever been translated into a modern language. 10%. That means the overwhelming majority of everything the Sumerians, Akkadians, Babylonians, and Assyrians ever chose to write down is, right now, sitting untranslated in storage drawers and display cases around the world waiting. Some of those tablets almost certainly contain administrative trivia, tax receipts, and shipment records nobody will ever find thrilling. But statistically, buried somewhere in that remaining 90%, there are almost certainly more works of literature, more personal letters, more scientific and astronomical records, and more historical accounts that have simply never been read by modern eyes. An AI system capable of translating at scale does not just save time. It has the potential to change how much of the ancient world we can actually access at all. Translation is not the only frontier where machine learning has been let loose on these tablets. a separate and equally fascinating project called Deep Scribe took a different approach entirely, tackling the problem from the direction of raw computer vision rather than language translation. Instead of working from tablets that had already been transliterated into a readable format by a human expert, the Deep Scribe researchers asked a more ambitious question. Could a machine learn to recognize cuneiform signs directly from a photograph, the way a person glancing at a page of handwriting might recognize individual letters, without any pre-processing at all? The team trained their system on 6,000 hand-annotated images pulled from a specific archive known as the Persepolis Fortification Archive, a massive trove of clay tablets written in the Elamite language around 2,500 years ago, discovered built into a fortification wall in ancient Persia. Those 6,000 annotated images allowed the researchers to identify roughly 100,000 individual signs, and the resulting predictive model achieved something in the neighborhood of 80% accuracy at recognizing and transcribing cuneiform characters directly from images. The long-term ambition behind this kind of research is almost science fiction in its simplicity. A portable device, something you could point at a tablet on a museum shelf or an artifact fresh out of an excavation trench, that instantly begins transcribing what it sees. It would be easy, at this point, to imagine that artificial intelligence has essentially solved ancient cuneiform, that the problem is finished and every remaining tablet is simply waiting its turn in some digital queue. The reality, according to the researchers actually doing this work, is considerably more careful and more interesting than that. A recent assessment from the Center for the Study of Manuscript Cultures at the University of Hamburg, one of the leading academic institutions studying these questions, offers a useful reality check. Their researchers note that artificial intelligence has already proven itself to be a genuinely significant support tool, particularly for a specific and very labor-intensive kind of work, linking together scattered references across an enormous digitized corpus. If the same personal name, or the same geographic location, or the same specific word appears on tablets held in 3 different museums on 3 different continents, a machine can spot that connection almost instantly, a task that might otherwise take a human scholar years of careful cross-referencing to notice by accident. But the same researchers are clear that this is fundamentally different from what people mean when they talk about true decipherment. Genuine machine decipherment, meaning a system that can independently crack a script nobody has ever read before without any existing translated examples to learn from, remains, in their words, still far off. The tools available today are trained on cuneiform that has already been read and translated by human experts. They are extraordinarily good at extending and accelerating human knowledge. They are not yet capable of generating that knowledge from nothing. That distinction becomes even sharper when you look at one of the most talked about developments in this entire field during the past year, a story that unfolded not around Sumerian, but around a different and even more mysterious ancient script called Linear A. Linear A was used by the Minoan civilization on the island of Crete, roughly 3,500 years ago, and unlike cuneiform, it has never been fully deciphered. Scholars can read some of its numerical and administrative content, but the underlying language it represents has remained genuinely unknown for over a century, one of the true unsolved puzzles of ancient linguistics. In June of 2026, a self-taught AI engineer and amateur linguist made headlines by claiming a breakthrough on exactly this problem. His method is worth walking through carefully, because it tells you something important about how these breakthroughs actually happen. He did not simply feed the entire Linear A corpus into an algorithm and wait for an answer to pop out. He started with a single, very human hypothesis, a hunch that one specific unknown word appearing in a prayer inscription might derive from a Semitic root, meaning to dwell or to inhabit, connecting Linear A to the same broad language family that includes Hebrew and Aramaic. Only after forming that hypothesis did he turn to artificial intelligence, using AI-built programming scripts to rapidly test whether that particular sound pattern held up consistently across the rest of the surviving Linear A corpus. According to his account, the approach allowed him to assign phonetic values to 40 individual signs and compile a working lexicon of around 408 words, results which, in his interpretation, suggest Linear A may be an extinct member of the Semitic language family after all. It is worth being precise about what artificial intelligence actually did and did not do in that story, because the honest version is more interesting than the exaggerated one. The AI did not have the idea. The human researcher did. What the machine provided was speed, the ability to cross-check one person's linguistic hunch against thousands of characters spread across an entire ancient corpus, compressing what would have been months or years of manual, line-by-line verification into a process that took a fraction of the time. Researchers who study computational approaches to undeciphered scripts have offered a fairly measured take on cases like this. Artificial intelligence, they point out, is genuinely powerful at large-scale pattern testing. at checking whether a hunch about one particular sign or word holds up consistently across an entire archive within minutes rather than years. It is also remarkably good at spotting repeated sequences that a human eye, however well trained, is simply prone to miss across thousands of fragments, and at restoring damaged or incomplete inscriptions, by statistically predicting what characters most likely once filled a broken gap. There is even a more exotic capability researchers refer to as cross-lingual transfer, in which a model trained extensively on one already known language can sometimes infer meaningful patterns in a closely related language that remains unknown, an approach that has already shown some real success with an extinct language called Ugaritic. But none of that changes the fundamental structure of the process. A human forms the hypothesis. A human decides what pattern is worth testing in the first place. The machine tests it at a scale and speed no person could match alone. It is important to add that the specific linear A claim from June 2026 remains genuinely contested within mainstream Assyriology and historical linguistics, and has not been broadly accepted as a confirmed decipherment. Extraordinary claims about cracking a century-old linguistic mystery deserve rigorous, patient scrutiny from the wider academic community before they can be treated as settled fact, and that process of scrutiny is still ongoing. This pattern, human insight paired with machine acceleration, rather than machine replacing human insight entirely, appears to be the honest shape of where this entire field currently stands, whether the script in question is Sumerian cuneiform, Akkadian, or Minoan linear A. It is also worth pausing directly on something that tends to spread far faster online than the careful, peer-reviewed version of this story ever does. Search around this topic for even a few minutes, and you will run into breathless claims that AI has been uncovering hidden, technologically advanced knowledge buried inside these tablets. Secret texts about ancient astronauts, beings called the Anunnaki, supposedly visiting Earth from another world, or shadowy references to genetic engineering disguised in mundane administrative language. Some of this content even reaches further, invoking quantum computing as the next great leap that will supposedly blow this decipherment work wide open, as though a fundamentally different category of computer is quietly standing by to finish the job. None of that holds up under scrutiny. There is no credible, peer-reviewed research connecting quantum computing to cuneiform translation at all, and the sensational claims about hidden ancient astronaut technology trace back largely to speculative content designed purely to generate clicks, not to the actual archaeological and linguistic record. The real tablets, the ones genuinely being translated by real AI systems built by real research teams, overwhelmingly turn out to contain exactly the kind of material you would expect from any ancient bureaucratic society: tax receipts, shipping manifests, complaints about business deals gone wrong, marriage contracts, and yes, occasionally, extraordinary literary works like the Epic of Gilgamesh. The truth here does not need embellishment to be remarkable. A 4,000-year-old bureaucratic society, so meticulous about record-keeping that we can now read a farmer's complaint about a bad batch of grain, is already a genuinely astonishing thing to hold in your hands. So where does this actually leave us right now, in the present moment? Artificial intelligence has not replaced the small community of human experts who have spent their careers learning to read cuneiform, and based on everything researchers in the field are currently saying, it is not about to. What it has done, and this should not be undersold, is fundamentally shift the economics of a task that used to be almost impossibly slow. Work that once demanded years of specialized training and painstaking manual comparison can now, in many cases, be assisted, accelerated, and cross-checked by machine learning systems in a matter of minutes. A translation engine trained on Akkadian can offer a working draft translation for a scholar to review and refine, turning the human expert's role from laborious first translator into careful expert editor, a shift that multiplies how much material one trained Assyriologist can realistically get through in a career. A computer vision system trained to recognize cuneiform signs directly from a photograph can help catalog and digitize the enormous backlog of tablets still sitting untouched in storage, the 90% that remain untranslated. And in genuinely difficult, ambiguous cases like linear A, artificial intelligence can serve as an extraordinarily fast and tireless research assistant, testing human hypotheses against an entire ancient corpus at a speed no individual scholar, however brilliant, could ever match working alone with pen, paper, and photographs. There is also something worth sitting with beyond the pure logistics of translation speed. Every one of these tablets was made by an individual person, pressing their own particular hand into wet clay on a particular afternoon for a particular reason. A merchant worried about a shipment of grain gone missing. A mother writing to a son stationed far from home. A scribe recording a legal dispute between two neighbors arguing over a shared wall. These are not abstract historical data points. They are, in a very real sense, the closest thing we have to eavesdropping on an actual conversation from 4,000 years ago, and until now, the vast majority of those conversations have simply never been heard by anyone in the modern world. That is the real weight behind this entire field of research. Quiet and unglamorous as the day-to-day work often is, it is not really about artificial intelligence proving how clever it can be. It is about giving a voice back to people who have been silent for longer than most of recorded history has even existed. There is a reasonable question worth asking here, which is where this actually goes next, realistically, over the coming years. The honest answer, based on where the research currently stands, is more digitization, more careful expansion of training data, and more collaboration between computer scientists and the small community of human experts who still hold the deepest understanding of these languages. Museums around the world are steadily photographing and cataloging tablets that have sat untouched in storage for decades, work that is itself a prerequisite for any machine learning system to eventually process them. Universities are training the next generation of both Assyriologists and computational linguists, often the same students, learning both disciplines at once, because the future of this field clearly belongs to people who can move fluently between ancient philology and modern machine learning. Funding bodies and digital humanities projects continue to expand the pool of transliterated text available for future training, which means every model built 5 years from now will almost certainly outperform the ones described here today, simply because the underlying data keeps growing. And slowly, tablet by tablet, fragment by fragment, that 90% of untranslated cuneiform inches its way toward being read for the first time since it was written. None of this is likely to happen with a single viral headline moment where a machine suddenly and dramatically finishes the job in one afternoon. That is simply not how serious, peer-reviewed research tends to work, however appealing that version of the story is to click on. What is actually happening is slower, more collaborative, and in its own way, considerably more remarkable, a genuine partnership between human insight and machine capability, steadily working through a backlog of ancient voices that has been waiting, in some cases, for literally thousands of years to be heard again. Every damaged fragment restored, every scattered reference linked across continents, every draft translation checked and refined by a human expert, adds one more sentence back to a conversation that started in the mud of Mesopotamia long before anyone thought to write anything down at all. Somewhere in a museum storage room right now, there is a tablet nobody living has ever read, holding a message from someone who has been gone for 4,000 years, patiently waiting for its turn.